Welcome to today's explainer, Recruit. I'll be your flight instructor, and right now, we're going to dive straight into the literal physics keeping you safely up in the sky. You see, flying? It's not magic. It's an absolute masterclass in applied physics. And by the time we wrap up today, you aren't just going to know what the buttons and pedals do. You're going to fundamentally understand the invisible aerodynamic forces that actually make those controls work.
But before I let you anywhere near those controls, you've got to understand our ultimate goal up there. We are constantly striving for one thing: equilibrium. It's this perfect, harmonious balance of opposing forces. Picture this. In steady, unaccelerated flight, your airplane's downward weight is exactly equal to the lift pushing it up. At the same time, the drag pulling you backward is exactly equal to the thrust pulling you forward. When you lock into that state, your aircraft is perfectly balanced, it's not speeding up, and it's not slowing down.
All right, grab your notebooks because here's today's flight plan for this explainer. 1. The four main forces. 2. Airfoils and lift. 3. Angle of attack. 4. The enemy called drag. 5. Wing flaps and control. And finally, 6. Propellers and thrust.
Okay, Section 1. The four main forces. Let's take a look at the basic tug-of-war happening every single second you're airborne.
Here's your battlefield. It is a constant, ongoing battle of lift counteracting weight and thrust pushing through drag. Now, you might actually think it takes a massive amount of thrust to keep a heavy plane up, right? Well, for the type of training airplanes you'll be flying, that upward lifting force is actually about 10 times greater than the drag in a steady cruise. We call this the lift-to-drag ratio, or L/D. So a ratio of 10 to 1 means that for every 10 pounds of weight we're lifting, we only have to fight 1 single pound of drag. It's honestly incredibly efficient.
Section 2. Airfoils and lift. Now, what's really fascinating here is how we actually generate that upward lift using a highly specific shape, something we call an airfoil.
To easily grasp how a wing actually works, I want you to ask yourself this. Have you ever stuck your hand out the window of a fast-moving car? You tilt your hand slightly up, and what happens? You immediately feel the rushing air physically push your hand up and back. That right there, that's aerodynamic reaction in its absolute simplest form. That physical sensation you feel on your hand is dynamic pressure, and it's the exact same force we harness to fly an airplane. Dynamic pressure depends entirely on just two variables: your speed relative to the wind and the actual density of the air itself. Think about it. If you drive your car faster, your hand gets pushed up a lot harder, right? Same exact thing goes for an airplane on the runway. As we accelerate, that dynamic pressure builds and builds until it's literally strong enough to lift thousands of pounds of metal right into the sky. And this brilliantly illustrates exactly how an airfoil gets the job done, totally relying on Bernoulli's principle. Notice the camber. That's the curvature on the top of the wing. As the wing pushes through the air, that curve acts almost like half of a Venturi tube. A pinched pipe that forces fluids to speed up. It forces the streamlined air over the top of the wing to accelerate. Well, Bernoulli discovered that as the velocity of a fluid increases, its static pressure drops. So by speeding up the air over the top, we create this zone of low pressure above the wing. Meanwhile, the higher pressure underneath effectively sucks the airplane upward. It's brilliant.
Moving on to Section 3, Angle of Attack. You see, the built-in shape of the wing isn't quite enough on its own. We have to talk about how you point that wing through the air.
Let's see how this all comes together. Imagine a perfectly straight line cutting directly through the middle of the wing, from the very front edge to the rear trailing edge. We call that the chord line. The angle of attack is simply the angle between that chord line and the oncoming relative airflow. And listen, this is your primary control for generating lift. By pulling back on the yoke, you increase that angle of attack, which forces the air to work harder and generates way more lift at lower speeds.
But as your instructor, I need you to hear this loud and clear and take it incredibly seriously. We rely completely on smooth laminar airflow clinging to the shape of that wing. Any contamination whatsoever, even a totally tiny, almost invisible layer of frost on the leading edge, completely ruins this delicate airflow. It causes the air to prematurely separate and tumble. This massively reduces your wing's lifting ability and, no joke, can literally prevent you from safely getting off the ground. Never, ever fly with frost on your wings.
And there's another way you can totally ruin that airflow, and that's by exceeding the critical angle of attack. If you pitch the nose up too high, usually past about 16 degrees in the planes we fly, the air simply can't follow the steep curve of the upper wing anymore. It violently separates, forming this huge turbulent wake. You completely lose your lift. We call this a stall. But don't panic. Airplanes are cleverly designed for this. When it happens, the center of pressure actually shifts rearward, which involuntarily yanks the nose of the airplane down. It's a built-in safety feature that naturally drops the angle of attack, helping you recover and get flying again.
Section 4, the enemy called drag. We really need to talk about the price we pay for all this incredible lifting power.
So, the crucial takeaway here is that you're actually fighting two totally different enemies up there. First up, parasite drag. This is pure physical friction. It's the air scraping against the skin of the plane and the turbulence caused by the plane's bulky shape. Just like sticking your hand out the car window, parasite drag gets exponentially worse the faster you go. Then you've got induced drag. This is the inescapable aerodynamic cost of creating lift in the first place. When high-pressure air from beneath the wing escapes around the wingtips into the low-pressure zone on top, it creates these massive swirling tornadoes called wingtip vortices. And because induced drag is directly tied to making lift, it's actually at its absolute worst when you're flying slow with a high angle of attack.
Notice how gliders, like this sailplane, handle this exact problem. Since they don't have an engine, they rely entirely on peak aerodynamic efficiency. To fight off that nasty induced drag, they use incredibly long, narrow, high aspect ratio wings. By making the wing ridiculously long, they push those drag-inducing wingtip vortices as far away from the fuselage as physically possible. This totally maximizes their lifting efficiency at slow speeds.
Section 5, wing flaps and control. So, how do we manipulate all these forces when it's time to stop cruising, slow the aircraft down, and actually return to the runway in one piece?
Take a look at these extended flaps on the trailing edge of the wing. When you lower them, you're literally temporarily changing the wing's fundamental shape. You're increasing the camber, and with certain types, like Fowler flaps, they actually slide backward, increasing the total surface area of the wing itself. This gives you a massive, immediate boost in lifting ability, allowing you to maintain that perfect equilibrium at much, much slower speeds.
Now, as a pilot, you're going to use these flaps in a two-step process in the landing pattern. First, as you enter the pattern, you drop partial flaps. This gives you that big boost in lift, letting you safely fly significantly slower without stalling. Then, when you're all lined up with the runway and ready to bring it down, you deploy full flaps. At full extension, they don't really give you much more lift, but they act like a giant, massive air brake. They create tons of parasite drag. This lets you point the nose down and fly a steep descent directly to the runway without gaining dangerous airspeed. Just a quick warning though, when you first drop them, that sudden surge in lift can cause the plane to essentially balloon upward if you don't adjust your pitch.
Finally, Section 6, propellers and thrust. To maintain our equilibrium, blast through all that parasite drag, and keep the air rushing over our wings, we need something actively pulling us forward.
The single most important thing to wrap your head around here is that a propeller isn't just a big fan. Actually, scratch that. It's essentially a highly engineered, twisted wing. It has a leading edge, a curved cambered surface, and a chord line, just like the main wings. The only difference is that instead of being pushed forward to create upward lift, the engine aggressively spins it in a circle to create forward dynamic pressure, pulling the airplane right through the sky. Now, you might be wondering, why on earth is the blade twisted? Well, the tip of the propeller is carving a much larger circle, meaning it's moving way faster than the inner hub near the engine. So, to make sure the entire blade maintains the most efficient angle of attack, engineers build this brilliant helical twist right into it, constantly changing the blade angle from the root all the way to the tip.
So, recruit, having mastered this explainer on the four forces, the airfoils, and the angles of attack, I really want to leave you with this one thought. The next time you look up at the sky and hear an engine roaring way overhead, are you just going to see a loud metal machine? Or will you finally understand the incredible, invisible tug-of-war, that absolute masterful orchestration of dynamic pressure, lift, and equilibrium that is literally keeping it alive? Class dismissed.